Welcome back to the deep dive. Today, we're plunging headfirst into the often unseen architecture that powers pretty much our entire digital world.
Mhm.
Think about it. Every online purchase, every streamed video, every swipe on your phone, it all relies on how data is stored and organized.
Absolutely. It's fundamental.
It really is. It's the silent, incredibly powerful backbone of our modern lives. So let's start unpacking this.
Indeed. Our mission today, well, it's really to demystify data storage and database design. We'll explore not just where your digital information actually lives, but also how it's meticulously organized for, lightning fast efficiency.
Right.
And why understanding these foundational concepts is absolutely crucial. Whether you're a business leader making strategic decisions, maybe a developer building applications, or just curious about how the digital universe functions.
Which many of us are.
Exactly. These insights are fundamental. What's truly fascinating, I think, is how these complex structures enable our daily digital interactions while sort of striving for elegant simplicity behind the scenes.
That's a great way to put it. Elegant simplicity hiding complexity. So whether you're prepping for a big meeting, catching up on a new field, or just insanely curious about the digital landscape, get ready for a deep dive into the fascinating world of data.
The foundations of data storage.
Yeah.
Where does all our information live?
Okay, let's kick things off with the absolute basics. What exactly is data storage?
Good starting point.
When we talk about data storage, we're really talking about the underlying technology specifically designed to, well, hold on to digital information over time.
Retention is key.
But it's more than just a digital attic, right? It's about making sure that anyone authorized to use that information can access it easily and effectively.
Yeah, accessibility and usability.
Allowing businesses to perform their daily activities with precision and speed. It sounds straightforward, but this is the bedrock upon which our entire digital economy rests.
That's spot on. And, imagine for a moment a world without robust data storage.
It's hard to even picture.
Businesses would literally grind to a halt. Every single transaction, your online banking,
Yeah.
a purchase at a store, even a simple text message, it would just vanish the moment it occurred.
Wow. No history, no record.
Exactly. Retrieving any past information, analyzing trends, or even just remembering a customer's address would be an impossible feat. It's not merely about archiving data. It's about making it instantly available and utterly reliable for continuous, seamless operation.
Okay.
It is, quite literally, the indispensable foundation. Without it, the vast interconnected systems we rely on every second would simply, well, cease to exist.
It really puts it in perspective.
And from a historical viewpoint, the evolution of data storage kind of mirrors the growth of civilization's need to record and recall information, from clay tablets way back when to these vast digital server farms we have today.
So if data storage is the foundation, then where does all this information actually live? You mentioned different types. Think of these as different kinds of specialized digital homes, or I like to picture them as different kinds of libraries, each with a unique purpose and a very specific way of organizing its books, so to speak.
Good analogy.
We've got what you might call the big four types of specialized data repositories that you'll often hear discussed.
Okay, let's break those down. First up, we encounter the Operational Data Store, or ODS for short.
ODS, got it.
This is essentially a high-speed, dynamic repository primarily designed for transactional data that flows in from multiple, often disparate sources across an organization.
Transactional, so like moment-to-moment stuff.
Exactly. It often serves an interim, highly active role, frequently sitting between the raw incoming data streams and the larger, more stable data warehouses we'll talk about later.
Okay, so it's like a busy train station for data.
Sort of, yeah. It's handling the immediate flow.
So we're talking about very active, real-time, minute-by-minute data here, right? Can you give us some concrete examples of what kind of information might live in an ODS?
Absolutely.
Yeah.
Think about a customer placing an order online that's a transaction, right? The details, the items, the price would likely flow into an ODS almost immediately. Or when a company processes a payment to a vendor.
Like paying an invoice.
Exactly. The payment details, vendor ID, amount, date, all that operational data. It could even encompass rapidly changing system-related data, like, say, monitoring the available storage capacity on a server in real time, or tracking network latency.
So system health monitoring, too.
Yeah, or counting the number of records a system has processed in the last hour. The ODS really captures the immediate pulse of daily operations.
Okay.
For a logistics company, for instance, an ODS might track the real-time location of trucks, package scans as they happen, delivery statuses. This allows operational managers to make instant decisions if, a delivery is delayed or a route needs adjusting based on traffic.
That real-time aspect is definitely crucial there. So ODS datasets are typically smaller than some other repositories we might discuss.
Generally, yes, compared to a full data warehouse.
And they're constantly being updated and overwritten, which means they're really designed for speed and currency, getting the latest info out fast.
Precisely. This continuous update mechanism where transactions are modified, processed, and then reported out almost instantaneously makes the ODS supremely ideal for those real-time operational needs. It ensures that the most current transactional view is always available to the business.
So it's less about looking back over years of data.
Much less. It's less about historical analysis and much more about providing that immediate, up-to-the-second snapshot needed for active business processes. Without an ODS, a sales team might see outdated inventory figures, or a customer service rep might not see the very latest update on a customer's inquiry. That would be bad.
Yeah, definitely frustrating for everyone. Okay, so from the ODS, which gives us that real-time pulse, let's transition to its much larger, more strategic sibling, the data warehouse.
Oh, yes, the data warehouse, a
Yes.
classic.
This is a very large, centralized repository. But here's a key distinction, right? It's used predominantly for reporting and long-term analysis, not for handling those daily, rapidly changing transactional purposes.
Correct. It's built for looking back and understanding trends.
It's where you go to look back at the big picture, understand trends over time, and inform strategic decisions, rather than, say, process a new sale right now.
That's right. A data warehouse typically pulls data either directly from those enterprise transactional systems we just discussed, or maybe it sources its information from an ODS after it's been cleaned and standardized.
So it's more curated data.
Often, yes. Once the data is pulled, it's combined and transformed into this single comprehensive repository, often structured specifically to optimize analytical queries. This combined data can then be used for a wide range of reporting needs to create more specialized data marts, or for other deep analytical purposes like forecasting.
Okay.
And this brings up an important question. Why bother separating transactional data from analytical data? Why not just do everything in one place?
Good question. Performance.
Performance is a huge one, and data consistency for historical analysis is another. Transactional systems need to be incredibly fast for real-time operations, processing maybe millions of small, rapid updates. Analytical systems, on the other hand, need to support complex queries across vast historical data sets without slowing down those live operational systems.
All right. You don't want your reporting to grind the checkout process to a halt.
Exactly. Trying to do both heavy-duty analysis and rapid transactions in one system would significantly slow down daily business. It's just not practical for most organizations.
Makes sense. So if the data warehouse is the main library housing vast amounts of historical data for general organizational analysis, what then is a data mart? Is it just like a smaller data warehouse?
A data mart is indeed quite similar to a data warehouse in its fundamental function supporting analysis, but it's much more focused.
A focused tab.
Instead of serving the entire organization with a broad range of data, it's tailored for a specific business purpose or a particular department. Think marketing, or sales, or HR, or logistics. Often, a data mart is actually a subset of a larger data warehouse, containing only the data relevant to that specific focus area.
Ah, okay. So like a specialized wing of the main library.
That's a perfect analogy. Imagine the main library has this vast collection, but the marketing department really needs a specialized section with only books on consumer behavior and advertising trends. That specialized section, that's your data mart.
That makes a lot of sense. So different departments within a large company might need really tailored, specific data to operate more effectively and answer their unique questions.
Precisely.
They would then select highly relevant data points from that massive data warehouse, the main library, and create their own specialized data mart.
Yep, they carve out their niche.
It sounds like it's all about empowering specific teams with data that's not only relevant, but also digestible and directly actionable for their unique needs without, overwhelming them with the entire company's data haystack.
Absolutely. It's about putting the right tools, the right data in the right hands. It streamlines their analytical processes significantly, reducing the time and complexity of getting the insights they need.
Okay, that clarifies the data mart. Now, moving on to what many consider the new kid on the block, or maybe the wild frontier of data storage.
You must mean the data lake.
The data lake, exactly. It's a repository that, like a data warehouse, holds a lot of information, but the crucial difference is that it contains both structured and unstructured data.
Right, that's key. Structured like spreadsheets, unstructured like images or text documents.
And primarily, it holds this data in its natural or raw format. So it's less like a neatly organized library and more like, well, a lake where everything just kind of flows in.
Yep. That's the crucial distinction, and it really changes everything about how data is managed and used. Unlike data warehouses, data lakes do not impose a predefined data structure or schema when the data is ingested, when it first arrives.
No rules up front.
Pretty much. This means the data isn't indexed, cleaned, or prepped into a specific format right away. Users can access it in its original raw form. This contrasts really sharply with the data warehouse's predefined schema, which is carefully put in place to enable quick processing and analysis of structured data.
Okay.
But what's truly fascinating here, and powerful, is the immense flexibility a data lake offers. By keeping data in its raw form, you don't have to decide upfront exactly how you're going to use it 5 years from now.
Ah, so it preserves future options.
Exactly, which provides immense flexibility for new types of analysis down the line, especially with emerging technologies like AI and machine learning that just thrive on vast, diverse data sets. For example, a data lake might store raw social media feeds, IoT sensor data streams, maybe video files, and customer transaction logs all together.
All mixed up.
Potentially, yes. Allowing an AI model, for instance, to discover unexpected correlations that a traditional structured database with its rigid schema might completely miss because the data wasn't structured that way initially.
That flexibility sounds incredibly powerful for innovation, for finding things you weren't even looking for. But on the flip side, does having all this raw, undefined data just sitting there in one place present any unique challenges, say for data governance or security, compared to the more structured environments like a data warehouse?
Oh, it absolutely does. That's the trade-off. The very flexibility that makes data lakes so powerful can also introduce significant challenges. Without a predefined schema or rigorous upfront processing and cataloging, data lakes can, unfortunately, become what's sometimes called a data swamp if they're not properly managed.
Data swamp. Doesn't sound good.
No, it isn't. It can become incredibly difficult to find specific data, to understand its quality or lineage, or even to ensure its compliance with privacy regulations like GDPR.
Right, because it's all just there.
Right. Exactly. Security also becomes a more layered concern. Different parts of the raw data might have varying sensitivity levels, requiring quite sophisticated access controls and monitoring. So while the potential for discovery is vast, it really requires robust data governance, metadata management, and security frameworks to truly harness its power responsibly. It's a balance organizations have to strike carefully.
That makes perfect sense. It's not a free-for-all. Okay, now let's shift gears slightly and talk about the evolution of where companies physically store all this data, whether it's an ODS, a data warehouse, a data lake, whatever. Traditionally, companies stored all their data on physical drives or servers right within their own data centers. We call this on-premises storage, right?
Correct. On-prem, for short. It was like having your own personal digital vault, completely under your direct physical control.
You own the hardware, the room, the cooling.
Everything. And while that offered a sense of direct control and potentially lower recurring costs once the initial, often massive investment was made, with the continuous rapid improvement in cloud computing technology and the truly exponential growth in data volume we've witnessed over the past decade or so, maintaining all that repository infrastructure on premises have become incredibly costly, complex, and frankly cumbersome for many organizations.
Yeah, I can imagine. Buying servers isn't cheap.
Not at all. Yeah. It requires massive upfront capital expenditure for hardware, specialized IT staff for maintenance and upgrades, constant vigilance about security, and ongoing efforts to scale up or down to meet fluctuating demands. It's a big operational overhead.
Which leads us to the cloud. This next evolution truly changes the game for many organizations. The shift from those massive upfront costs and ongoing maintenance headaches to a more flexible pay-as-you-go model.
A cloud model, yeah.
Cloud technologies allow data to be securely stored in or easily migrated to the cloud. This means cloud-based storage is highly scalable. Companies can store as much or as little data as they need, expanding or contracting capacity almost instantly.
Elasticity, they call it.
Right. And they can consume and process that data with incredible agility, accessing it from anywhere with an internet connection. It's like having a utility for storage where you only pay for what you actually use rather than buying and maintaining your own power plant, metaphorically speaking.
That's a great analogy. And this shift has profound practical implications for businesses globally. It enables much easier global access to data for distributed teams, significantly improves disaster recovery capabilities by easily replicating data across multiple geographically dispersed data centers.
Which is huge for business continuity.
Absolutely. And it drastically reduces the IT overhead associated with managing physical infrastructure, the servers, the networks, the cooling, the real estate.
So IT teams can focus elsewhere.
Yes, exactly. Furthermore, cloud providers often offer very advanced security features and compliance certifications, things like KPI or PCI DSS, that are incredibly difficult and expensive for individual companies to achieve and maintain on their own. It allows companies to focus more on their core business innovation rather than the complexities and capital drain of data center management.
But are there downsides,
Oh.
concerns?
Of course. It also introduces potential concerns around vendor lock-in, getting tied to one specific cloud provider, and the need for robust cloud security expertise within the organization, plus managing ongoing operational expenses. It's not free, it's just a different cost model.
Relational database design, the structured backbone of information.
Okay, so we've covered where data lives
Yeah.
in these different kinds of digital homes, from the highly structured data warehouses to the, well, less structured data lakes.
Mm-hmm.
But once it's there, especially the structured stuff,
Mm-hmm.
how do we make sense of it all? How do we organize it in a way that's not just stored, but truly useful, queryable, and ensures its integrity over time?
Now we get to the heart of structured data management.
Enter relational databases.
Exactly. Relational databases are truly one of the most elegant, efficient, and frankly effective methods developed for storing structured data. In fact, many of the repositories we just discussed, like data warehouses and operational data stores, are very often designed and built upon relational database principles.
So they're foundational even for those bigger systems.
Often, yes. They remain the most common method for managing structured data precisely because of the numerous, undeniable benefits their underlying data model provides. It offers a level of consistency, integrity, and query power that's, well, hard to beat for many use cases.
So how does this differ from something simpler, like, say, a flat file?
Mm-hmm.
If you've ever tracked a simple list of contacts or maybe inventory in a basic Excel spreadsheet,
Yeah, many people start there.
where names, addresses, phone numbers are all just in one big list without any clever links to separate company info or order histories, you've essentially experienced a flat file.
Yeah.
It's just plain text, or maybe a simple table, with no inherent defined connections between different kinds of information within the file itself.
Right. Everything's just flat.
Think of a relational database, then, as a meticulously organized, multi-drawer filing cabinet. It's got clearly labeled drawers, cross-reference files inside, where each piece of paper knows exactly where it belongs and how it relates to others. That's compared to just a single giant pile of documents where you have to dig through everything manually to find what you need and hope it's consistent.
That filing cabinet analogy perfectly illustrates the core difference and why relational databases are so powerful. The benefits are really substantial and directly address common business pain points.
Okay, like what?
First, completeness. It's not just about having some data, it's the guarantee that every single piece you need for a complete business process, every order detail, every customer's current address, every product specification will always be there and perfectly linked.
So no missing pieces when you need them.
Ideally, yes, that's the goal. It stops you from ever trying to solve a puzzle with missing or incomplete pieces. If you're processing a customer order, you know you'll have the customer shipping address and the product's price all connected and readily available because the database structure enforces that connection.
Makes sense. What else?
Second, no redundancy, or at least minimal redundancy. Storing redundant, repetitive data is something we actively try to eliminate in relational design. Why?
Wastes space?
It does waste resources, both storage space and processing power, when you run complex reports. But more critically, it introduces a significant risk of data entry errors and inconsistencies.
Right. If it's in two places, which one is correct?
Exactly. When data is duplicated, updating it becomes a nightmare. You might update one instance but forget the other, leading to conflicting information and a loss of that assurance of having one version of the truth. Normalized relational databases demand that each unique element of data be stored in only one definitive place.
The single source of truth idea.
Precisely. Third, business rules enforcement. Relational databases can be meticulously designed to actually help enforce internal controls and business rules automatically.
How so?
For example, you can design a database to prevent an invalid entry from being stored, like ensuring a product quantity can't be negative, or that a customer ID entered on an order actually exists in the customer table. This minimizes human error and ensures data quality right at the point of entry.
Built-in checks and balances.
You got it. And finally, communication and integration of business processes. When designed correctly, relational databases support business processes across the entire organization by providing a shared, consistent view of information.
Breaking down silos.
Exactly. This naturally results in vastly improved communication across functional areas. Sales, marketing, inventory, accounting can all work from the same trusted data and leads to much more integrated and streamlined business processes. It really helps the left hand know what the right hand is doing.
Those benefits really highlight the precision and reliability that relational databases bring. And the way they achieve this, you said, is by storing data across a series of related tables.
That's the fundamental structure.
Each table, in turn, contains columns, also known as attributes, and rows, which are referred to as records. And each column, or attribute in a table, must be both unique within that table and entirely relevant to the table's specific purpose.
Exactly right. Let's define those building blocks a bit more clearly. When we talk about tables, we're referring to the fundamental organizational structures within a relational database. They establish columns and rows to store specific types of data records. During the initial design phase, these tables are often conceptually called entities. The very existence of more than one table, designed to be related to each other, is the first key differentiator from those simplistic flat files you mentioned earlier. Each table is a focused collection of information about one type of thing.
Okay, to give you a clear picture, if you were building a database for a typical sales process, you wouldn't just have one giant spreadsheet listing everything.
No, definitely not.
Instead, you'd have separate tables or entities for customers, maybe another for employees, one for sales orders, and perhaps another for inventory or products.
Logical separation.
The customers table, for instance, would store all the data relevant to each customer, just the customer stuff, names, addresses, phone numbers, maybe loyalty status. It keeps everything incredibly neat, organized, and prevents you from having to repeat all those customer details every single time they place an order.
Right, you just refer back to the customer record. And within these tables, we have attributes, which are simply the columns. Attributes describe the characteristics or properties that you want to know about each entity.
The details about the thing.
Exactly. So in our customers table example, last name, first name, and email address would all be attributes. Each attribute in a table must be unique to that table and directly relevant to its purpose, ensuring data is logically grouped.
Then we have records, which are simply the rows in a relational database table. Each record contains a complete set of information about one specific instance of an entity within that table.
One complete entry, yes.
So in our customers table, a single record or row would contain all the information about one particular customer, their unique ID, first name, last name, address, phone number, and so on.
That's right. One row, one customer. And at the intersection of a column attribute and a row record, we find a field.
The individual box.
Pretty much. This is the specific, smallest unit of data in the database where a single data value is entered. For example, in the customers table, the field at the intersection of the last name column and a specific customer's row would contain just that customer's last name, like Smith.
Okay, tables, attributes, records, fields. Got it. Now here's a crucial detail that I think often gets overlooked by those new to databases. Each attribute or column in a table has a designated data type.
Ah, very important.
This could be numerical, text, date, time, character, decimal. This isn't just about categorizing. It fundamentally specifies how the data is stored, what kind of values are allowed in that field, and just as importantly, how it can be analyzed or manipulated later.
Understanding data types is absolutely vital. It's foundational because they dictate what operations can be performed on the data and ensure its basic integrity.
How so? Give me an example.
Okay, so attributes that represent a truly meaningful numerical value, something you'd actually want to do math on, like the cost of an item, a quantity sold, or maybe an employee's salary. These must be classified as numerical data types. things like int for integers, or decimal for numbers with decimal places.
All right.
This ensures that the data in those fields can function correctly in mathematical equations, allowing you to perform critical calculations like sums, averages, variances, stuff that's vital for business analysis and financial reporting.
Makes sense.
Conversely, if you tried to, say, add up customer phone numbers,
Which look like numbers.
right, they contain digits, but they aren't mathematically meaningful in that way. They're typically stored as text or varchar. The database, because of the data type assigned, would prevent you from performing mathematical operations on them.
Gotcha. So if you accidentally put a phone number, which contains digits but isn't meant for arithmetic, into a numerical field that is designated for calculations, the system might try to add it up or average it, which obviously makes no sense.
Exactly. Or it might just throw an error and refuse to store it. Data types prevent those kinds of fundamental misinterpretations and enforce data quality right at the point of entry. It's a really critical guardrail. And speaking of fundamental guardrails, let's talk about database keys. These are absolutely essential.
Keys, like primary keys.
Primary keys, foreign keys, yes. They are essential for uniquely identifying records within tables and, crucially, for facilitating the relationships between different tables. They are what allow your meticulously organized filing cabinet drawers to, cross-reference each other seamlessly, creating that integrated view of information we talked about.
The magic links.
Pretty much. Every table in a well-designed relational database is required to have a primary key, PK. This is typically a single column, though sometimes it can be a combination of columns.
A composite key.
Yes, we'll get to that. The sole purpose of the primary key is to ensure that each row in that specific table is absolutely, definitively unique. It's often referred to simply as a unique identifier.
So no two rows can have the same primary key value in the same table.
Never. Interestingly, a primary key is rarely descriptive of the data itself. Instead, it's usually an artificially generated collection of letters or, more often, just sequential numbers. Think of a student ID number, an online order number, an invoice number, or an account number.
Right. My order number doesn't describe what I bought.
Exactly. These are unique tags assigned to each record, not descriptions of the student or the order. It's the singular identifier that tells the database, this row is distinct from every other row in this table. Now, sometimes, a single attribute isn't enough to uniquely identify each record in a table. This happens especially when you're dealing with intermediate tables that link other entities together. In such cases, multiple attributes are combined to form that unique identifier. This is called a composite primary key.
Okay, can you give an example?
Sure. Think about a course enrollment table in a university database. Neither student ID alone nor course ID alone might be unique. Why? Because a student can take multiple courses, and a course can have many students. But the combination of student ID and course ID would uniquely identify a single student's specific enrollment in a specific course. So student ID, course ID together would form the composite primary key for that table.
Got it. Uses two pieces to make one unique ID.
Correct. Then we have foreign keys, FK. These are really important for establishing those relationships. A foreign key is an attribute or set of attributes in one table that refers back to or matches the primary key in another table.
Right.
Let's return to our customer ID example. Customer A would be the primary key in your customers table, uniquely identifying each customer record.
Right.
However, that same customer ID would likely appear as a foreign key in your sales orders table.
So the sales orders table needs to know which customer placed the order.
Exactly. And here's where it truly gets powerful. That link, the primary key in the customers table connecting to a foreign key in the sales orders table, is what creates the relationship between those tables.
That's the connection.
That's the connection. It allows all that structured data to talk to each other seamlessly. So a single customer ID might appear multiple times in the sales orders table.
Because one customer can place many orders over time.
Precisely. The foreign key customer ID in the sales orders table essentially points back to the customers table, letting you easily look up all the customers' descriptive information, their address, phone number, loyalty status, without having to duplicate all that info in the sales orders table itself every single time.
That's the core of how relational databases avoid redundancy and maintain data integrity across vast amounts of information.
You've got it. Foreign keys exist specifically to implement and enforce those relationships. Whenever two tables need to be connected logically, one of them must contain a foreign key that references the primary key of the other, establishing a clear, unambiguous link between related pieces of data.
Okay, this is making sense. But with massive amounts of data flowing through these systems and all these interconnected tables with primary keys and foreign keys, how do you keep track of what's what? How do you ensure everyone involved, from the database administrators maintaining it to the data analysts trying to use it, knows exactly what each piece of data represents, what its purpose is, and how it relates to everything else?
Excellent question. That's where the data dictionary comes in. It's absolutely crucial.
The instruction manual.
Essentially, yes. A data dictionary is absolutely paramount for helping database administrators effectively maintain databases and, maybe even more critically, for analysts to identify, understand, and accurately use the data they need for reporting and insights. It's a type of metadata, which simply means data about data.
Data about data. Okay.
Its fundamental purpose is to provide and summarize comprehensive information about all the data elements in a database. The tables, the columns, their types, their meanings. It makes it significantly easier to work with that data, understand its nuances, and grasp how it can be used to inform accurate decisions and build meaningful reports. Think of it as the ultimate detailed instruction manual for your database.
This sounds so critical because, as you mentioned earlier about data types, technology will do exactly what it's told, but it doesn't understand context or meaning.
Right. It just processes.
So if you, as an analyst, look at an attribute called, say, amount, and you think it means sales amount, but the data dictionary would tell you it actually means discount amount.
Oh.
You can make some serious analytical mistakes and draw completely inaccurate business conclusions, even if the data itself is technically complete and has integrity. It really highlights the indispensable need for human understanding guided by clear definitions.
Absolutely. It is an industry best practice and, frankly, a critical necessity to get to know the data thoroughly. You do that through things like database schemas, which show the structure, and, crucially, data dictionaries, which explain the meaning, before attempting any serious data analysis or reporting.
Due diligence for data workers.
Definitely. A comprehensive data dictionary, especially when working with complex relational databases, can include a wealth of information. The precise attribute names, sometimes cryptic, detailed textual descriptions of what each attribute actually represents in business terms, whether it's a key, PK or FK, and its role in relationships, whether the field is required for data entry, can it be blank, its exact data type, INT, varchar, date, etc., if there's a default value and what it is, the field size or character limit, and any other relevant notes or business rules necessary for full understanding and proper use. It's truly the database's ultimate guide, ensuring everyone speaks the same data language.
Normalization and database models, ensuring data integrity and structure.
Okay, so we've established that relational databases aim for data that's complete and, crucially, not redundant. They do this by organizing information into these linked tables using keys.
That's the goal.
But how do database designers actually achieve that elegant, non-redundant structure? How do they decide what goes in which table? This brings us to a fundamental and incredibly important technique called normalization.
Yes, normalization. This is a core concept in relational database design. It's a meticulous technique specifically aimed at reducing data redundancy. But it's really more than just saving space. It's the art of systematically stripping away every single redundant piece of data and ensuring its logical consistency across the database.
Getting rid of duplicates.
Fundamentally, yes. But it's also vital for eliminating undesirable characteristics that can creep into poorly designed databases. Things like insertion anomalies, where you can't add certain data unless some other unrelated data exists. Or update anomalies, where changing a piece of data requires updating it in multiple places, risking inconsistency. And deletion anomalies, where deleting one piece of data unintentionally wipes out other, unrelated but necessary data.
Wow, those sound like serious problems.
They can be huge headaches. The process of normalization involves systematically dividing larger, potentially messy tables into smaller, more manageable, and logically linked tables. The core purpose is to assure that data is stored not just efficiently, but with the highest possible integrity, where each distinct piece of information exists in only one authoritative place. Imagine building a complex machine where every single bolt and gear is unique and perfectly placed, eliminating clutter and ensuring that any change you make ripples through precisely as intended. That's kind of what normalization does for data. It's the secret to data integrity and often leads to better performance and maintainability in large systems.
To simplify this concept, I remember hearing a memorable analogy often used in database design, borrowed from that movie, A Few Good Men.
The courtroom scene.
Exactly. We adjust the famous line, the truth, the whole truth, and nothing but the truth, to describe tables in a relational database and the attributes within them. So for databases, it becomes the key, the whole key, and nothing but the key.
I like that. It's catchy and maps well.
It's a useful way to remember the core principles behind these rules, which are laid out in what we call the three normal forms, or 1NF, 2NF, 3NF. Let's break down what each part of that analogy means in terms of these forms.
Sounds good. The first step in this process is achieving first normal form, 1NF. This is the foundational level, the absolute minimum for a relational table. It's essentially about making sure your data is atomic, meaning indivisible and properly identified. This inherently makes sorting and filtering data much, much easier later on.
Atomic, what does that mean here?
It means each cell or field in a table must contain only one piece of information, just one value per column for any given row. You wouldn't, for instance, have a single cell in a phone number column containing 555-1234-555-5678. That's two values.
So no comma-separated lists in a single field.
Correct. Each phone number would need its own row or perhaps its own dedicated column if structured differently, but one value per field. Each value should be indivisible from the perspective of that attribute.
Okay, one value per box. What's the other part of 1NF?
The second criterion is that each record, each row, in every table must be uniquely identified. This is accomplished, as we discussed, with a primary key, which could be a single attribute like customer ID, or a composite primary key if multiple attributes are needed to guarantee absolute uniqueness for that record.
So 1NF really just sets the stage, ensuring your data is granular, not multi-valued in single fields, and properly identified from the get-go. It makes it easier to work with, search, and filter. This is the key part of our analogy, right? Meaning you simply have a designated primary key to identify each unique record.
Precisely. It's the basic entry requirement for a relational table. Once a table is in 1NF, the next normalization step is to conform the data to second normal form, 2NF.
Okay, 2NF.
Now, 2NF is particularly meaningful and really important for tables that have composite primary keys. Remember, those keys made up of two or more attributes acting together.
Right, like student ID and course side.
Exactly. 2NF requires that all non-key attributes in a table must depend on the entire primary key, not just part of it. If you have a composite primary key, every other piece of information in that row needs to be fully dependent on all components of that primary key combined.
Dependent on the whole thing.
Okay,
Yeah.
let's use that university example again to illustrate. Imagine a student courses table with that composite primary key, student ID, course ID. An attribute like grade achieved would likely pass the 2NF test. Why?
Because the grade depends on which student and which course.
Exactly. The grade a student achieves is specifically tied to both that particular student, student ID, and that specific course, course ID. It depends on the whole key.
Makes sense.
However, consider an attribute like course title. Let's say we put that in the student courses table too. Would that pass 2NF?
The course title. Well, that only depends on the course side, doesn't it? You don't need the student ID to know the name of the course.
Precisely. Since course title only depends on course ID, which is just part of the composite key, it violates 2NF if it's in that table. It indicates that course title should reside in its own separate courses table, where course ID is the primary key.
Oh, okay. So this connects directly to the whole key part of our analogy. It's not just about having a key, but making sure that everything else in that row truly needs all parts of the key to make sense and be uniquely identified there.
You got it.
So if I'm picturing this, 2NF is essentially saying, if you have a multi-part ID, every other piece of information in that row has to depend on all parts of that ID, not just one section of it. If a non-key attribute can make sense just by looking at a portion of a composite key, then that's a signal telling you it probably belongs in its own separate table, linked by that portion of the key.
Exactly. It helps you logically separate information into the correct tables, like saying a specific car parts quantity on an order depends on both the order number and the part number, the whole composite key. But the part name only depends on the part number, part of the key, so the part name shouldn't live in the detailed order line item table. It belongs in a separate parts table, linked by part number.
Okay, that clarifies 2NF and the whole key.
Okay.
Now finally, once a table is in both 1NF and 2NF, the next normalization step is to ensure that each non-key column in a table describes only the primary key. This is the goal of third normal form, 3NF.
Right. 3NF tackles a different kind of dependency.
How is it different from 2NF?
3NF wants to establish that none of the non-key attributes depend on other non-key attributes.
Mm.
These are sometimes called transitive dependencies. It's about dependencies between non-key columns.
Dependencies between non-key columns. Okay, explain that.
Let's go back to our university example. But look at the students table this time. Let's say it has student ID as its primary key. It also contains advisor ID as a foreign key, which is perfectly fine. That links the student to their assigned advisor.
Okay. Student depends on student ID. Advisor depends on student ID. That seems okay.
Right. But now, what if that same students table also had an attribute labeled advisor name?
Hmm.
Advisor name.
Would that violate 3NF? Think about what determines the advisor's name.
Well, the advisor's name depends on the advisor ID, not directly on the student ID.
Exactly. Advisor name depends on advisor ID, which is a non-key attribute in the students table, not directly on the primary key student ID. The student's name depends on student ID, sure, but the advisor's name depends on the advisor ID. Attributes that violate 3NF in this way are called transitively dependent columns. They depend indirectly on the PK through another non-key attribute.
Okay. This must be the nothing but the key part. It's making sure there aren't any sneaky indirect dependencies hanging around that could introduce redundancy or inconsistencies down the line. That's a perfect way to think about it.
If an attribute depends on another non-key attribute within the same table, it essentially means you're storing information about one thing, the advisor, in the table meant for another thing, the student, instead of just using the advisor ID foreign key to refer to the advisor and letting a separate advisors table handle the advisor's name and other details.
Precisely. It keeps the data clean, avoids duplication, you don't store the advisor's name, potentially hundreds of times, and ensures that if an advisor's name changes, you only have to update it in one place, the advisor's table, not potentially across thousands of student records where it might be stored redundantly.
That seems much more efficient and less error-prone. So it's almost like a rigorous tidying up process for your data tables. I can imagine if you don't follow these normalization rules, especially 3NF, you end up with what some people call data spaghetti, right? Things tangled up where they shouldn't be.
You absolutely do. Data spaghetti is a perfect description for an unnormalized or poorly normalized database. Without normalization, you risk having data that's hard to maintain, prone to update errors, susceptible to deletion anomalies, and often incredibly inefficient to query.
Give me that update example again.
Sure. If advisor name was stored redundantly in the student's table and an advisor got married and changed their name, you'd potentially have to find and update every single student record associated with that advisor. If you missed just one, you'd have inconsistent data about that advisor's name in your database.
Right, Mayor.
With proper normalization, 3NF achieved, the advisor name is only in the advisor's table. You update it once there, and all linked student records automatically reflect the change implicitly because they only store the unchanging advisor in MAIDI. It's crucial to remember, too, that these normal forms are progressive. To qualify for 3NF, a table must first satisfy the rules for 2NF, and 2NF requires adherence to 1NF. It's a structured, stepwise process, building layer by layer to achieve optimal data integrity.
Key, whole key, nothing but the key. Got it. Okay, so we've talked about why data is structured using normalization to ensure integrity and avoid redundancy, but now let's shift to how that structured normalized data is actually designed and then implemented. How do designers go from an abstract idea, like these normal forms, to a fully functional living database that organizations use every day? This brings us to the concepts of database models and schemas.
Right. This is where we bridge the gap between the abstract design principles and the tangible reality of a working database. It's really important here to distinguish clearly between a data model and a database schema, as the terms are sometimes used loosely.
Okay, what's the difference?
A data model is generally a higher-level, conceptual representation of data structures within an information system. It's typically abstract and focuses more on understanding the logical relationships between different pieces of data and representing business requirements. It's not necessarily limited to relational databases. It's more about understanding the overall information landscape of an organization.
So the blueprint.
Kind of like the architect's conceptual blueprint, yes. A database schema, on the other hand, is the actual implementation and concrete execution of that data model's design within a specific database system. It's a precise set of instructions for the database engine on how to physically organize the data, defining the exact tables, columns, data types, constraints, indexes, and relationships.
So the schema is the detailed construction plan.
Exactly. If the data model is the blueprint showing rooms and their purpose, the schema is the detailed construction plan and specification, detailing every beam, pipe, wire, data type, and index, ready for the builders or the database system to start. And these data models themselves are typically created in distinct stages, progressively increasing in detail and precision as the design matures. They usually start with the conceptual data model, which is the least complex and most abstract.
Big picture view.
Right. Then move through the logical data model, adding more detail about attributes and relationships.
Getting more specific.
And finally, into the physical data model, which is the most detailed and completely implementation-ready, tailored to a specific database technology. Each of these models is appropriate for different audiences and serves a distinct purpose in the overall design process.
Why different models? Why not just jump to the detailed one?
Because different people need different levels of detail. The vast amount of technical specification in a physical data model isn't necessary and might even be confusing for a business stakeholder who just needs a high-level understanding of the main data elements and how they relate. But that technical detail is absolutely critical for a database administrator who needs to build the database, optimize performance, or for a developer writing code against it.
Okay, that makes sense. Let's unpack each of those stages then. What does a conceptual data model look like, and who typically uses it?
A conceptual data model is your highest level big picture representation. It defines the main entities. Remember that those are like our tables, the core things we care about, like customers, products, orders, and the basic relationships between them.
But no details.
Deliberately, yes. It intentionally omits the nitty-gritty details of specific attributes, columns, or how it will be physically implemented in a database. Its primary use is to understand the overall scope and structure of the data across an organization, and critically, to communicate that high-level design clearly to non-technical business stakeholders.
So everyone agrees on the main concepts first.
Exactly. It's often used in the very early stages of a project. And because it's so high level, it can be incredibly simple, sometimes even just drawn on a whiteboard or paper with a pencil, making it really easy to modify during initial discussions and gather feedback quickly. For instance, a simple conceptual model for a sales process might just show 5 boxes labeled: customers, sales orders, products, employees, and department, with lines showing how sales orders are related to customers, employees, and products. It just provides that initial overview to get everyone on the same page about what information needs to be stored and how it broadly connects.
Okay, so it's about getting the core entities and their high-level connections right, making sure everyone agrees on the fundamental pieces of the puzzle before diving into the excruciating details. And then we move to the logical data model. What's the step up in detail here?
Yes, the logical data model is a significantly more detailed representation of the data structures, but still described at the level of the data itself, generally independent of any specific database technology, like Oracle, SQL Server, etc.
More detail, but still abstract-ish.
Kind of. It goes beyond just entities and relationships. It defines the attributes, the columns, for each entity, and crucially, it includes the designation of primary keys, PKs, and foreign keys, FKs, that establish the relationships.
Ah, so keys show up here.
Absolutely.
Yeah.
This is also the stage where normalization rules, like 1NF, 2NF, 3NF we just discussed, are often applied more rigorously. If the initial conceptual model had started with some attributes, the logical model would then carefully identify the primary and foreign keys in each entity and adjust any entity relationship structures to resolve issues related to normalization, ensuring that the data structure is logically sound and minimizes redundancy before thinking about physical storage.
Can you give an example again?
Sure. Building on our sales process model, the logical model would show not just customers and sales orders entities, but also their specific attributes, like customer ID, marked as PK,
Yeah.
customer name, customer address in the customer's entity. And in the sales orders entity, you'd see sales order ID as PK, maybe order date, and then crucially, customer ID, marked as FK, explicitly showing the link back to the customer's entity.
So it shows how they connect.
Exactly. It clarifies precisely how normalization works to prevent duplication. For instance, you'll notice that the product description isn't included directly in the sales orders details entity, even though you might want to know it for analysis. Why?
Because it's transitively dependent, belongs with the product.
Right. It can be looked up via the product ID or SKU foreign key relationship between the sales order details entity and the products entity. The logical model explicitly shows how these defined relationships allow data lookup rather than redundant storage. While it's significantly more detailed than a conceptual model, it's still generally database agnostic, meaning it's not quite ready for direct database implementation yet. This model is primarily used by data architects, business analysts, and developers to ensure the logical consistency and integrity of the data design.
And finally, the physical data model, I assume this is where all the nitty-gritty, ready-to-build details come in, specifying exactly how it will manifest in a real database system.
Precisely. The physical data model is the most detailed representation of the data structures. At this stage, entities are explicitly referred to as tables and attributes as columns, because this model is designed to be complete enough that the database can be built directly from its description, often using automated tools. And importantly, it is database specific.
Meaning it considers the specific database software being used.
Yes. Different database systems, like Oracle, MySQL, PostgreSQL, SQL Server, have slightly different data types, features, and constraints. The physical model accounts for these specifics. In addition to specifying all tables, relationships, and all primary and foreign key identifications, it also includes many of the granular details you typically find in a data dictionary, now formalized for implementation.
Ah, so this is where we see the actual data types for each column, like whether something is an INT or varchar, and maybe even character limits. This is the real blueprint for the database engineer, or DBA.
Exactly. For instance, an INT data type would be specified for whole number values, like quantity ordered. For primary keys like order D, even though summing them isn't meaningful, they might still be stored efficiently as INT or sometimes varchar, depending on the system and format. Varchar would indicate a variable length string or text value with a specified maximum character limit of 50.
Okay.
Date or datetime is a special numerical type that enables calendar-based calculations and functions, crucial for tracking things like when orders were placed or shipped. Decimal 1022, or numeric 102, specifies values for numbers that aren't limited to whole numbers, like unit price or sales amount, indicating storage for a total of 10 digits with 2 allowed after the decimal point, again ensuring they support mathematical operations accurately. And text, or sometimes varchar in varchar string, depending on the system, represents any non-numeric value, even if it's a string of digits that aren't meant for mathematical interpretation, like a phone number or a ZIP code or product description. This granular level of detail makes the physical model an invaluable guide for direct database implementation and also for later fine-tuning system performance by adding things like indexes. This progression clearly shows how each model stage adds more and more fidelity, getting closer to the actual nuts and bolts of a functioning database.
So to summarize these data models then, conceptual is the high-level sketch, table names, relationships, for business understanding. Logical adds the keys and attributes, focusing on normalization and logical structure, mostly database agnostic. And physical gets down to the specific database technology, defining exact tables, columns, data types, constraints, indexes, everything needed to actually build it.
That's a perfect summary. You won't see an effective logical model that completely lacks the characteristics of a conceptual model, nor a physical model missing the logical attributes. They're progressive layers of detail, each building on the last and serving a different audience and purpose in the design and implementation lifecycle. Now, shifting focus slightly again. While normalization, leading to models like the 3NF one we discussed, is fantastic and typically the standard for transactional, operational, relational databases, like an ODS or the back end of an e-commerce site, because it prioritizes data integrity and avoids redundancy. Data warehouses and data marts. Those repositories built primarily for analysis and reporting often utilize different database schemas once the data model is set and ready for implementation. These schemas are designed specifically to optimize performance for analytical queries, even if it means sacrificing strict normalization sometimes.
Okay, so different schemas for different purposes. What are the main ones for analytics?
The two most popular schemas for these analytical environments, designed for performance and reporting, are the star schema and the snowflake schema.
Star and snowflake. Heard those terms.
These dimensional modeling schemas revolve around two primary types of tables, fact tables and dimension tables.
Facts and dimensions.
A fact table contains the core measures or metrics, the quantitative data points, often referred to as facts. These are the numbers that measure your business performance. Things like sales amount, cost of goods sold, quantity sold, profit, clicks, impressions.
The numbers you want to analyze.
Exactly. Fact tables usually don't contain much descriptive text themselves, but crucially, they hold foreign keys that link them to the dimension tables, which provide the context for these measurements. Think of fact tables as containing the what happened in your business numerically.
And the dimension tables then must provide the context for those facts, giving meaning to the numbers, right? Like who, what, where, when.
Precisely. Dimension tables contain the descriptive or contextual data for those measures in the fact table. Think of attributes like dates with columns for year, quarter, month, day, maybe day of week, product names with category, brand, color, customer names with demographics, location, geographical locations, city, state, country, region, or employee names with department title.
Ugh.
For example, a time dimension table might store all the calendar attributes needed to slice and dice sales figures by year, quarter, month, or day. A product dimension would hold all the descriptive data about each product, its product category, brand, color, size. These are the who, what, where, when, and maybe how surrounding your business events recorded in the fact table.
Got it. Facts are numbers, dimensions are descriptions. So diving into the specifics of those schemas, what's the STAR schema all about and why is it so popular?
The star schema is by far the most common and also generally the simplest schema for dimensional modeling. The data is organized with a central fact table, and it's surrounded directly by its associated dimension tables.
Like a star with points.
Exactly. If you diagram it out, it forms a shape that visually resembles a star, with a fact table sitting at the center and the dimension tables radiating out directly around it. Each dimension table is connected directly to the fact table via a single foreign key join.
Sounds clean.
It's very straightforward to understand and navigate, which makes it quite intuitive for business users doing reporting or analysis. Its simplicity also means that analytical queries typically involve fewer table joins, just joining the fact table to the needed dimension tables, which generally leads to excellent performance for reporting, as the data is somewhat denormalized specifically to optimize read speed.
Denormalized, meaning it breaks some normalization rules.
Often, yes, particularly within the dimension tables themselves. For instance, a product dimension in a pure star schema might store category name and subcategory name directly in the product table, even though technically subcategory name depends on category name, a transitive dependency violating 3NF. It duplicates that category info for simplicity and performance.
Okay, sacrificing normalization for speed and ease of use. And then there's the snowflake schema. How does that differ from the star, and what are its particular strengths or weaknesses?
A snowflake schema is similar in concept to a star schema. It still has fact and dimension tables, but its dimension tables are further normalized.
More normalized than the star?
Yes, instead of having potentially wide, somewhat denormalized dimension tables like in a star, the dimension tables in a snowflake schema are broken down into multiple related tables, forming a more complex hierarchical structure, much like the intricate branching patterns of a snowflake crystal.
Ah, hence the name.
Exactly. For example, remember how in a star schema, a product dimension might have product name, product subcategory, and product category all in one table.
Right.
In a snowflake schema, product subcategory and product category might be moved into their own separate dimension tables. DIM subcategory, DIM category, linked back hierarchically to the main DIM product table via foreign keys. So DIM product links to DIM subcategory, which links to DIM category.
So more tables, more links.
Correct. This makes the snowflake schema inherently more complex to query than the star schema, as it requires more tables and therefore more foreign keys to link everything together, leading to more joins needed for many analytical queries, which can sometimes impact performance.
Sounds like a downside. What's the upside?
The upside is that it can be more flexible for managing complex dimensional hierarchies, and it typically uses less storage space, because this normalization reduces data redundancy within the dimension structures themselves. You don't repeat the category name for every product in that category only once in the DIM category table. You can think of it as striking a balance at cheaper. It's more normalized than a star schema, offering better data integrity for complex dimensions, but still generally less normalized than a full 3NF relational model used for transactions. Its strengths lie in better data integrity and reduced redundancy within those complex dimensions, but often at the cost of slightly more complex queries and potentially slower performance for some analyses compared to a star.
Okay, star is simple, fast, maybe a bit redundant. Snowflake is more complex, less redundant, maybe slower queries sometimes. So what does all this mean for the end user, especially those folks doing business intelligence or recording with tools like, say, Tableau or Power BI? What are the practical trade-offs for organizations choosing between these?
That's an excellent question, and it's really where the rubber meets the road, where the real-world trade-offs become clear for businesses. Dimensional modeling in general, using either star or snowflake schemas, is typically much easier for business users to understand and query directly compared to a highly normalized 3NF relational model.
Why is that?
Because the data is organized intuitively around clear business concepts, the facts, what we measure, and the dimensions, how we measure it. This makes it very user-friendly for reporting and analysis. People think in terms of show me sales fact by region and product category dimension.
Right, it matches how they ask questions.
Exactly. And most modern business intelligence tools like Tableau, Power BI, Clear, Looker, they work exceptionally well with star and snowflake schemas precisely because of this straightforward business-oriented structure. They can quickly render dashboards and reports by simply joining a central fact table to a few relevant dimension tables, which is usually very efficient.
Okay, so good for users, good for tools. But what's the catch?
However, and this is a really significant point to remember, since dimensional modeling, especially the star schema, often result in denormalized databases, meaning data might be intentionally duplicated across different dimension tables for performance or ease of use. It inherently loses the strict one version of the truth advantage that fully normalized 3NF relational databases provide.
Ah, the redundancy comes back to bite you.
It can. Data will be redundant in a denormalized data model, even if only slightly within the dimension tables of a snowflake schema. So whenever a change is necessary in the source transactional system, like a product category gets renamed or sales region is redefined, that change might need to be carefully propagated and updated in multiple places within the dimensional model during the data loading ETL process. If that process fails or misses something, you can get inconsistencies.
Okay.
This raises an important strategic question for any organization building an analytical system. What's more important for your specific analytical use case and your data governance requirements? Is it the ultimate data integrity and minimized redundancy that comes with strict normalization? Or is it the ease of use and potentially faster query performance for business users that comes with dimensional modeling like Star or Snowflake?
A fundamental design decision.
Absolutely. It's a fundamental design decision with real implications for data management strategies, ETL complexity, and analytical capabilities down the line. Often what you see in practice is organizations using a highly normalized 3NF database for their operational transactional system to ensure integrity there, and then replicating and transforming that data into a Star or Snowflake schema in a separate data warehouse or data mart, specifically optimized for analytical reporting. That way, they try to get the best of both worlds. Outro.
Wow, well, what a journey we've been on. From the raw, untamed storage of data lakes all the way to the meticulous organization of relational databases.
Quite a spectrum.
And then navigating through the intricate dance of normalization, the key, the whole key, nothing but the key, and finally looking at the practicalities of schema design with stars and snowflakes. It's truly amazing how much thought, engineering, and strategic decision-making goes into managing the vast amounts of information that really power our modern world.
Indeed. It's easy to take for granted, but there's a huge amount of structure underneath. We've seen how different types of data storage serve very specific purposes, from real-time operations to long-term analysis. We've explored how relational databases ensure data integrity and connectivity through keys and normalization principles,
Right.
and how data models and schemas then guide the very construction of these complex systems, translating business needs from a high-level concept into a concrete, functional implementation. Understanding these concepts helps us not just appreciate the technology, but also critically assess the information we encounter every day, whether it's a simple online transaction confirmation or a complex business performance report. It provides a useful lens through which to understand the very structure of the digital world around us.
Absolutely. So the next time you place an online order or stream a video or maybe just check your bank balance online, you'll hopefully have a deeper appreciation for the unseen architecture humming along behind it all. You'll know about the decisions that likely went into its design and maybe even some of the compromises or trade-offs that were probably made along the way.
Every system embodies those choices.
So here's a final thought for you, our listeners, to ponder. Given the truly exponential growth of data we're seeing, the increasing demand for real-time insights, and of course the rapid rise of AI and machine learning, how do you think the trade-offs we discussed today, particularly between data redundancy for ease of use, like we see in star or snowflake schemas, versus that strict one version of the truth goal of deep normalization, how might those trade-offs evolve in the future?
That's a fascinating question. Will AI allow us to somehow have the best of both worlds more easily? Or will entirely new architectural paradigms, things people are talking about now, like data meshes or data fabrics, fundamentally change how we even think about data storage and database design in the first place?
Right. What new challenges and opportunities will all this present for businesses, for developers, and even for us as individuals navigating this data-driven world?
A truly fascinating question to ponder indeed. The landscape is constantly shifting, that's for sure, but these core principles we discussed today will likely continue to adapt and remain relevant even as the technology evolves. Thank you for joining us on this deep dive. Until next time, keep exploring.
Absolutely. Keep those questions coming, keep thinking critically about the data around you, and we'll keep digging. See you on the next deep dive.